Hey everyone, I'm Nick and welcome to another episode of Fundamentals of GPU Architecture. So in this video we're going to expand on what we talked about last time, which was, the high-level programming interface for things like GPUs using CUDA. And we're going to see how that actually translates down to first a virtual instruction set and then finally a machine instruction set. And we'll also look a little bit at OpenCL, which is more typically used for AMD GPUs rather than NVIDIA ones. So let's go ahead and get started. So again, with all of these things, it all starts back at the very beginnings of GPUs with purely graphics-oriented things. So instructions of virtualization for GPUs, it really started with OpenGL and their OpenGL shading language OGSL, and then also Microsoft's high-level shading language HLSL. But CUDA came around 2007, so a similar path. They had their own high-level virtual instruction set architecture. And so for NVIDIA GPUs, this is called Parallel Thread Execution, ISA, or just PTX for short. So this is a fully documented virtual instruction set, so you can go to the NVIDIA site and you can see, the semantics of all these instructions and, what to kind of expect from them. And then, this virtual instruction set itself is used in a very common academic simulator, so that's used for hardware research, called GPGPU-Sim. So GPGPU-Sim allows you to simulate new architectures for GPUs. So, as that kind of implies, it doesn't run on a GPU, it runs on a CPU, and it uses this virtual instruction set, and it gives you a functionally correct simulation. So there's a performance model in there, but then there's also a functional model. So not only do you get the performance numbers that you can use to kind of judge whether or not new architecture is good, but it will actually be running this PTX instruction set, and it will give you the desired result as if you did run it on a on hardware, right? So if you did vector add or something, or like Saxby in the simulator, you would get the same result at the output. It would just take quite a bit longer. So it's not a replacement for GPUs as far as running GPU code. Okay, so PTX is pretty similar as it is a RISC instruction set architecture like ARM or MIPS or Spark, which means it's pretty easy to understand, unlike more complex things like a CISC architecture like x86. And so we'll actually see that, and we'll look at what that Saxby program that we saw above, or in the previous video, how does that translate into PTX? So let's go ahead and so let's give kind of a refresher. So here's our Saxby code. The only thing that's going to be PTX here is, of course, the actual Saxby function itself. Everything else is just going to be run on the CPU, so that requires no special, that's kind of out of the scope of GPU architecture or GPU programming. So really just cared about what this turns into, that's into PTX, or how this is turned into PTX rather. So that's our CPU code, or rather our high-level CUDA code. So just as a reminder, so it's a CUDA kernel, so that's denoted by this global, and then we pass it some things, and then we figure out what position the thread is within a grid right here. We make sure that we're not off the actual number of elements inside of our vectors that we pass in, and then we just do Saxby, right? Every thread does their own version of Saxby. So let's see how this looks in PTX. Again, the virtual instruction set. So it's not terribly difficult to understand, but it is a little more verbose. So we've got these parameters, right? And these parameters are just what we're loading in as far as our arguments to the kernel. So we've got an U32 and a floating point number, and then these two U64s. So these are just going to be our pointers, right? 64-bit pointers. Then we'll have this floating point 32, so that's going to be our A value of Saxby. And then this U32 is just the size of those vectors, which is an int that we passed in, right? So if we go down to the actual code that gets executed, right? So we've got, this is just loading our parameters. So LD param, pretty easy to understand. Then we'll go ahead and get our block and our thread dimensions here out of these special registers. So CTA ID, so cooperative thread array, like I said last time, it's another word for thread block. So CTA ID NTID and TID. So, we use these to calculate, where we are, within the grid, which is what this multiply and add does instruction. And then we have this set P. So set P stands for set predicate. And so basically what this does is it evaluates some operation that's greater than or equal, that's denoted right here. And then it sets a predicate, in this case, predicate 1. And then we evaluate that predicate here, right? And so based upon how we evaluate that predicate, either, this is that if statement in there. So either we do nothing, so we go all the way here, right, and just to the return part of the program, or we actually do Saxby, right? So this big part right here is the actual Saxby. So we see we've got some global loads that we're doing here. Then we also have, a store to main memory, so that's after we do Saxby. And then we've got some, addition and multiplication right here. So again, this is just, how Saxby looks in terms of PTX, right? But it's fairly easy to understand. So let's kind of go back up here. So what do we? So is PTX the bottom level? No. So what happens is, like I said, this is a virtual instruction set. So before runtime, this gets converted into SAS, which stands for streaming assembler. And this, this process of using an assembler, this is either done by the GPU driver or a standalone program such as the PTX assembler, PTXAS. And so this is provided by the NVIDIA CUDA toolkit, so you can have, so just like in VCC that you use to compile your programs, you can use PTXAS to assemble, PTX code. The only catch is that SAS, what it gets translated into, isn't fully documented. So while you can write, all the code you want PTX, you can't write all the code you want in SAS because it's not fully documented, meaning you don't really understand what every instruction does or how it may modify state or what the actual semantics are. So, but there has been a significant amount of research that's gone into this. So things like, very early days. So back in 2007, a project called dCUDA. And so this is really for the first kind of iteration of CUDA, figuring out what these SAS instructions did, and to such a point where you could actually develop an assembler for it. So then, this was even supported on the simulator. So the simulator that now typically only does PTX code, or a modified version of PTX called PTX Plus, but we'll leave that out for now. It could actually run the machine instruction set at that time. So eventually there was a tool released called CU Object Dump, similar to Object Dump if you're familiar with that in the CPU world, where you could actually get the SAS code out of a binary, or the PTX code if you want. And they started to partially document SAS because, of course, it's really important. If you're a GPU programmer, you understand what your code is doing. So they did document it somewhat. But, as of April last year, so about a year ago now. So only a partial list of opcode names and then no detail on operand formats exist or the actual instruction semantics. So the fact that we need higher and higher performance stuff has led to other projects like dCUDA. So this project right here called MaxAS, from Maxwell Assembler, where it was actually the SAS instruction set was actually completely reverse engineered such that another assembler could be made for academic purposes. This guy Gray. So 2.4 illustrates the SAS code compiled for Fermi architecture, so a very early architecture. And so we'll just go through this paragraph and then we'll look at the code. So so let's see what we have here. So it looks like it's just going to talk about the code. So let's go down there. So let's look at 2.4. And so you can see that it is significantly different than the PTX code. But there's still some things you can pick out, right? So, like here, you can tell here's our CTA and our thread ID information. We're doing, this multiply and add operation here to calculate, our position of a thread in a grid. And then we're setting a predicate. So this is integer set predicate greater than or equal. And so exactly what these means and all these specifiers that can pile up and pile up and pile up. This is something that the reverse engineering work has to go into and kind of tell what it's doing. But basically, they're setting this predicate 0, right, and this PT. So these are getting set based upon evaluation of these greater than or equal an and operation between all of these, right? So this is basically just used to this is that if statement comparison here. And then of course we have a branch, right? So instead of branching to so up in the PTX right here, we've got this branch to BBO2. Here we have a branch to a specific location, so 0x78, which is right here, which is an exit call, right? And then over here, this is just going to be Saxby, right? So we've got some memory locations here that we're loading in, and then stores, like I said, loads, multiply and add operations, fuse, multiply, add operations, right? So this is just computing Saxby though. And like I said, this is for Fermi architecture, which is denoted by SM20. So let's go back to that paragraph and skip over the code part. So a little bit different, but the main difference you can see is, up at the PTX code, we had, kind of parameter space where we specifically had, load param, right? But, this didn't really exist in the SAS code. So the reason why it doesn't exist is because in SAS, parameters are allocated, while they're allocated in their own separate parameter space in PTX and SAS, kernel parameters are just passed in banked constant memory, which can be accessed by non-load store instructions in SAS. So this is in constant memory. We don't have to do this explicit loads like we have in the virtual instruction set. So then we have it a lot different. So we'll look at another compilation of the same PTX code to a different machine ISA. So that was for SM20. We'll look at it for a later SM version. So we can go ahead and do that now after a little bit of talk. So, the actual machine ISA changes significantly sometimes between generations. So there are even some lines that you'll see that there is some, encoding there, but there's no disassembled instruction, right? And so it turns out what they started doing, what NVIDIA that is they started embedding special control instructions, not associated with the specific, executed instruction, but a control instruction is just something that they added, introduced in the Kepler architecture to eliminate the need for dependency checking using a scoreboard. So they basically took scoreboard logic and they put it in instructions instead. So it's part of the instruction stream. So, this has been explored by a couple people. Let's see. So, there's, according to the MaxAS, the guy that did that, Gray, there appears to be, one control instruction for every 3 regular instructions in Maxwell, which appears to be the same in Pascal. Not quite sure for Volta and Turing. Likely it's the same, but it could have changed. So there's also, the 64-bit control instruction. So what does it typically do? So it's generally grouped into 3 parts. So 21 bits. Maxwell contains 3 groups of 21 bits each, encoding the following information for each of the following 3 instructions. So it'll include a stall count, a yield hint flag, and a write, read, and wait dependency barrier. So basically they're just taking the logic of, how long do you have to stall, and, whether or not you have to yield, and then if you have read or write dependencies there, that's just all encoded within that instruction. And then also, if you're familiar with my This Week in Architecture series, where we talked about register file caches, so they also embed things into the assembly itself, such as this R0.reuse, so register reuse cache or operand reuse cache that they have. That's also embedded in the as a modifier to the actual operands. So we'll look at an example of that. So this short multiply add instruction, we'll see an example of that. So this operand reuse cache, like we explained in This Week in Architecture, This operand reuse cache appears to enable register values to read multiple times for each main register file access, resulting in reduced energy consumption or improved performance. So see that other video if you're interested in that. But let's look at the actual disassembly there, right? So here we have the disassembly. As you can see, it's far different than the original disassembly for SM20. So this is for SM60 architecture, so Pascal architecture. So as you can see, there's about every 3 instructions, right? There's a special instruction here, which isn't associated with an actual instruction because it's just encoded dependencies, right? So that's what, we've got that here, we've got another one here, etc. And like right here, we've got this reuse. So this is saying use the operand reuse cache. So, between the actual machine ICEs, there can be a huge difference. But, in the PTX code, the PTX is kind of abstracted away from that. So we can kind of ignore the underlying changes. The assembler has to worry about, doing that pass of the PTX and converting it into SAS. All right. So it's a lot on the PTX side of things. But, you can still, it's still fairly readable though, even if we don't know explicitly what it's doing. So we've got, we still have CCTAD and TID here. We've got some new modifiers, right, that are a little bit tricky, and I don't know what they are off the top of my head. But we see a set predicate here, and, based on the set predicate, so this is going to be that if statement, which leads me to, everything past here, right, is going to be, this is actually going to be the Saxby part, right? So this is going to be the Saxby part of the program. Okay, so let's talk about AMD now, right? So AMD and the graphics core, next instruction set architecture. So in contrast to NVIDIA, so while NVIDIA didn't release a machine instruction set or hardware level ISA, AMD did, right? For Southern Islands, first generation AMD's GCN architecture. So this is really helpful to academic researchers developing simulators because, you explicitly know, what is actually being executed on the GPU. So a key difference between this GCN architecture and the NVIDIA GPU architecture, though, is a separate scalar and vector instruction pipeline, right? Now this is actually changed then because I believe Turing has a scalar pipeline as well. But you might be wondering, well, why would I have a scalar pipeline, right? What's the point of having a scalar pipeline? Well, so you have big vector instructions, right? So you're doing Saxby. You've got all of these things that are, computing, different operations on different pieces of memory. That's great for a vector pipeline. Now, let's say that you have, I don't know. So let's say that, you pass in a value A and a value B and to your function, and you compute A plus B, right? So this will be done by every single thread, but it doesn't need to be done by every single thread, especially if you launch a ton of threads. You're computing a single value there, right? You're not computing, a bunch of different values touching a bunch of different pieces of memory. Every thread will evaluate the exact same number. So, if you have a scalar pipeline, you can kind of avoid that, right? You can have only, say one thread, or that scalar pipeline just computes that single value instead of having every thread waste a bunch of energy computing the same value. Okay, so in figure 2.7, which we'll look at a little bit, scalar instructions are prefaced with an S, and vector instructions are prefaced with a V. So in AMD GCN architecture, each compute unit, so this is going to be a core compared to an SM in NVIDIA's, contains a scalar unit with 4 vector units. So vector instructions execute on the vector units and compute different 32-bit values for each individual thread in a wavefront. So wavefronts are just groupings, reminder of 64 threads. So in contrast, scalar instructions execute on the scalar units and compute a single 32-bit value shared by all threads. Okay, so let's continue on. In the example shown in figure 2.7, so let's go ahead and look down here, right? So here's so OpenCL code based upon figure 2.2, so that's from a while ago, but here's the OpenCL version, right? So it's pretty similar, right? So here's some function here. Notice it's not CUDA semantics, but we have if A is greater than B, you return A times A minus B, else return B times B minus A. And so then you see down here, it's annotated, so you've got vector and scalar instructions here, depending on what the compiler says to do, and then you have two different control flow paths, right? So you have this if path, and then this else path, right? So in the example shown in Figure 2.7, the scalar instructions are related to control flow handling, right? So that as far as control flow goes, A greater than B will be the same for everybody, right? Because float A, float B, those are constant for everybody. So you really only need to execute that once. So let's see. So in particular, exec down there in the that low-level GCN assembly is a special register used to predicate execution, so kind of like those P registers in CUDA, of individual vector lanes for SIMT execution. And so like we said, we've got groupings of a bunch of threads together, all kind of going in lockstep. So sometimes, not all 64 threads will be doing the same thing. And so we have to use kind of this mask that tells us which threads should be active at any given point. Because remember, the programmers have this idea that things are they're scalar threads, so they can all go a different way as far as control flow goes. So the use of masking for control flow handling GPUs is described in more detail in 3.1.1. All right, so once we get into the core, we'll actually we need to see physically how does that, or at least from a hardware level, how do we actually do this though? All right. So so AMD's GCN hardware instruction set manual. So there's interesting insights into the AMD hardware. So if we know the low-level machine instruction set, we've got better insights into what they're actually doing and what the hardware has to do. So an example of this is to enable data dependency resolution for long latency operations. There includes this swait count instruction for each wavefront there. So for each wavefront, there are 3 counters. So vector memory count, local global data store count, and then a register export count. And then these indicate the number of outstanding operations of a given type. The compiler programmer inserts this instruction to have the wavefront wait until the number of outstanding operations decrease below a specified threshold, right? So this is how they manage these things. Well, we just kind of believe these encoded instructions from NVIDIA's side of things. So that's going to go ahead and do it for this episode, though. So next time we'll actually get into the SIMT core, right? Instruction and register data flow. A little more interesting than the high-level programming model, but it's kind of necessary. As always, feel free to check me out on GitHub at github.com/coffee4arch, where I've got all my CUDA codes, C++ code, teaching stuff, and even in the readmes there, I have linked to the videos and then the individual things that I use. And then if you want to follow me on Twitter, I've got one of those as well. Okay, so that's going to go ahead and do it. Again, my name's Nick from Coffee Before Arch, and I hope you have a nice day.